Dear students, in this video we will discuss some fundamental aspect of HCP structure, that is arrangement of atoms in different lattice sites, calculation of total number of atoms in a unit cell, relation between lattice parameter and height of an unit cell, and finally calculation of packing factor. Now this picture shows the location of atoms at different lattice sites and picture of total unit cell of hexagonal close packed structure. Now here we are observing the hexagonal unit cell having lattice parameter A and height of this cell as C. In this case, the lattice parameters A, B, C are not equal. The relation is like this: A equal to B is not equal to C. Now, in this hexagonal structure, the base and top surface, they are in the form of hexagon. So definitely for a hexagonal structure of this type, there are 12 corners. So number 1, 2, 3, 4, 5 and 6. Similarly, on this top surface, we have the 6 corners: 1, 2, 3, 4, 5 and 6. In this way, 12 corners are there. So we are observing here, atoms are located at these 12 corners and also the base centered positions of these hexagonal faces. So this is the top hexagonal face. We are observing here the one atom is located at the center. Similarly, at the bottom hexagonal face, we are observing another atom located at this center. With these atoms, further one more layer is there, which is totally inside the unit cell, and this layer forms these 3 atoms. So number 1, 2 and 3. So in this way, we are observing here total lattice sites are 12 plus 2, 14 plus 3, 17. Now, this is the geometrical picture of arrangement of atoms in a hexagonal unit cell. The nearby picture shows the real positions of atoms in such a unit cell. Now, the top hexagonal base we are observing here, at the face centered position of this hexagonal base we are observing one atom, and at 6 corners we are observing 6 atoms. Similarly, the same thing will be repeated at the bottom surface. But in between these two surfaces, one layer is there which possesses 3 atoms, and these 3 atoms are totally inside this unit cell. Now, considering this fact of this arrangement, we'll try to calculate the total number of atoms present in a unit cell. So let us see how to calculate the total number of atoms in a unit cell. So we'll write here the formula to write total number of atoms in a unit cell equal to contribution of corner position atoms to the unit cell and total number of corner position plus contribution of base center position atoms multiplied by total number of base center positions plus number of atoms inside the unit cell. Now we know that this can be calculated simply. Contribution of corner positions is 1 by 6. So here we are observing 1 by 6 into total number of corners are 12 plus contribution of base centered position atom and total number of base centered position. Here 2 represent total number of base centered position plus contribution is 1/2 here, and these 3 represent the total number of atoms present inside the unit cell. So in this way, 1 by 6 into 12, this is 2, 2 into half, this is 1 plus 3, this is 6. So this indicates that the total number of atoms in a unit cell are 6 in HCP structure. Further, second parameter we will try to study here, relation between lattice parameter A and C of an unit cell. Now we have already observed that the edges of an hexagon we have treated as A, and height of the cell we have considered as a C. So here we are having the picture indicating one hexagonal base. From this hexagonal base we are observing 6 equilateral triangles. So 1, 2, 3, 4, 5, 6. Out of these equilateral triangles, we have taken out one triangle, that is A, B and G. Using this structure, you can easily show, that is, the relation between lattice parameters A and C is equal to numerically root 8 by 3. So we are going to use this relation for the calculation of packing factor. Now next one, let us will calculate the packing fraction of HCP unit cell. Now again we are observing here the HCP unit cell structure, and this indicate the positions of atoms. Concentrate on middle layer 3 atoms, that is located at M, N, P, and base centered atoms at O. What happens here? This forms the tetrahedron. So the base centered atom and the 3 mid layer atoms form a tetrahedron MNOP, which has sides equal to A, that is this is A, and height of this unit cell, height that is from this to this, is C by 2, that means height divided by 2. Using this tetrahedron, it can be shown that for an ideal hexagonal crystal, C by A ratio is equal to under root 8 by 3. Therefore, now using the fundamental formula of atomic packing factor, one can write APF equal to volume of atoms in unit cell divided by volume of unit cell. So this can be calculated as total number of atoms 6 into volume of a single atom, that is 4 by 3 phi r cube, divided by 3a square c sine 60. So further, to simplify this relation, it is necessary to use the relation A equal to 2r, where r is the radius of an atom and A is lattice parameter, age of an hexagon, and second relation necessary to use C by A ratio root 8 by 3. So substituting these values and simplifying this equation, we'll be able to get the atomic packing factor equal to 0.74. That means in closed pack structure, the packing factor is equal to 0.74. This also we have observed in FCC structure also. Thank you.